So our first talk will be given by a brilliant PhD student from UC Berkeley, who is a core developer of the vLLM project, which is one of the most used high-performance open-source LLM inference engines out there, with dynamic batching, page detention, custom kernels, speculative decoding, quantization, and many other features. They, together with she together with their incredible team, have been pushing the boundaries of what's possible in open source and available in terms of inference speed and efficiency, always minimizing latency and maximizing throughput. Please give a warm welcome to Lily Lu.
Thank you, thank you. Hi everyone, I'm Lily. I'm currently a PhD student from UC Berkeley. So it's a great honor to represent the vLLM team to talk about our project in CUDA mode. It's a great event, and other team members of vLLM is actually also here, like Kai Chao, Usuk. Feel free to catch up with them like if you get time. Okay, so let me get started. Okay, so for this talk, it will mainly have three topics. First, I will introduce vLLM project, and next I will highlight two features, like two new features in vLLM. The first one is torch compile. The second one is speculative decoding. So the goal of the vLLM project is to build the fastest and easier to use open source LLM inference and serving engine. So we launched the project in June 2023, and when there were only very few like open source projects for LLM serving. And we are very lucky because we get lots of traction from the beginning, and it has become one of the most popular projects in this field. And we have lots of like users, industry users, including like those big cloud companies like Google, AWS, or Azure. So why do people use vLLM? I think one of the reasons is that vLLM has very easy to use APIs. So we have the LLM class, and the user just need to specify the prompts and the model they want to use, and then it just call the .generate function on those prompts. And under the hood, the vLLM will handle the scheduling, handle the KV cache management, do the request batching automatically. So user does not need to worry about those things. So we also we also support vLLM as an OpenAI API compatible server. So the users can just serve the vLLM, use like vLLM serve, and specify the model you want to serve. And then you can just use the OpenAI client, send the request to the endpoint. You just replace the URL with the local URL. Another strength of vLLM is very broad model support. So vLLM currently support almost all the popular like OpenLLMs and vLLMs. So we are the official launch partner of Llama. So we support Llama new models from day one. And we are also have very close collaboration with those like state-of-art vision language model creators. Like for example, Pixtral and Qwen, like they contribute their like new vision language models to vLLM. On top of that, I think vLLM also supports many features. Right? First, we support various like quantization methods, including like FP8, GPTQ, AWQ. We also have the LLM compressor so that the users can compress their models, use different like compression methods. So vLLM also support like prefix caching. So this can be an important feature if like lots of prompts they share the same like system prompt. So in that case, we can reuse the KV cache of their input of those system prompts. So we also support like pipeline parallelism. So pipeline parallelism is important when the model is too big to fit in a single node. Or you want to serve like models with some PCIe connected instance such as L4. And lastly, we also support like multi-LoRa serving. So you can serve multiple LoRa adapters in vLLM. We can load those adapters to the GPU memory dynamically. So actually, we provide like many more features, like besides what I mentioned before. So in today's talk, I will dive into a little bit about torch compile and speculative decoding. But we also have like trunk prefill, guided decoding, KV cache offloading. So I encourage you to take a try if you are interested. So of course, vLLM is built for performance and efficiency. So in LLM serving, there are 5 types of kernels you might want to like implement your custom kernels instead of writing pure PyTorch, right? So here, vLLM supports like different types of kernels. So for example, for the quantized gem, we find Catalyst kernels provide the best performance. And for group gem, we find that Triton is more beneficial in that case. So we use the Triton kernels for those group gen, and they are used in the MOE serving in vLLM. We also have like a custom or reduced kernel for small batch size in vLLM, because we find that Nico's ring or reduce is not very good in those small batch size scenarios. We also have different like attention backend, right? Like flash attention, flashing for OX formers. So for all those kernels, we all use like CUDA graph to minimize the host overheads. But building an inference engine is much more than just write kernels. Like in the process of building vLLM, we learn a tough but valuable lesson. So we learn that to fully utilize the GPU, we need to pay close attention to everything happening on the CPU. GPUs are fast, but CPUs are not. So LLM's inference engine is doing much more than just running the model, right? We do like tokenization, detokenization, scheduling, memory management. All those logic happens on CPU, and in vLLM, it happens in Python, right? So which are might be even slower. So if they are not handled correctly, they might become the performance bottleneck. And that is what we have experienced. So vLLM is currently undergoing some rearch, and we also have lots of like multi-step scheduling, asynchronous output processing to reduce those overhead. So I encourage you to check out our recent blog post. So we do hope that vLLM is not only feature-rich, but also become very performant. So lastly, I want to highlight that vLLM is a community project. So we are joining the Linux Foundation, and we are hosting like regular meetups and office hours with our collaborators and users. Next, I want to talk a little bit more about Torch Compile. Let's dive into it. So I think since the start of the Torch Compile, vLLM is very actively integrating this feature. But we find that since vLLM is a big project, you cannot just write a Torch.compile, a single line of code to do the integration. So we actually divide our integration plan into 4 steps. So let's go over them one by one. So the very first way we integrate Torch Compile is to apply it locally. So for example, models often have have slightly different layer norms in terms of like precision or operation order. So instead of developing a custom kernel for each layer norm, we just use Torch Compile for those slightly different like layer norms, and treating it like a Triton kernel generation. So this is already a big win for us because we don't need to write any kernels ourselves. We just use Torch Compile. However, to unlock more optimizations, we want to apply Torch Compile more broadly. So the second step is we want to use Torch Dynamo to capture the full model. So in the second step, we capture the entire model, but the challenge there is that we need to register every customer operations in a way that Dynamo could process. So we want to avoid unnecessary like recompilation, and we also have some special handles for those like in-place custom ops. Next, we are enabling Torch Inductor to optimize those captured graph. So we hope that with those with the torch inductor, we can optimize the performance using some Trident kernels for those small gems, and it can do the operation fusion more aggressively and do more like memory efficient memory planning. So looking ahead in Q4, we want to explore further optimizations with Torch Compile. So for example, we want to add some custom compiler passes for new types of operation fusion, like fusing the app logs, prologs of the quantized kernels. So please stay tuned for this one. So lastly, we want to highlight that vLLM is a multi-hardware platform. So currently, we support like 4 different types of hardware, include different types of different GPUs, CPUs, and custom AI chips. So, and this is possible because of the we rely on we have a very close integration with like PyTorch. So instead of relying on some like external compilers or formats like Onyx, we just use PyTorch as a narrow waist. So it's a middle ground to connect different backends with hardware agnostic models and utilities. Okay, so for the last part, I will just go through another feature currently we are actively working on in vLLM, which is speculative decoding. So before I dive into the feature, let me give you a recap, like what is speculative decoding. So we think it's an important feature because it's a feature to help reduce the LLM inference latency. So the intuition is that like some tokens are easier to generate than the others. So instead of using the large language model to generate all the tokens, we use some small model to like propose tokens to generate the easy tokens and the large model to generate difficult ones. So to give you a more concrete example, so like here, given a prompt, we will generate the, like without speculative decoding, we generate the token one by one, auto-regressively. But with speculative decoding, we will send the prompt into a small model first, and the small model will propose token auto-regressively. It will say, oh, the output might be T1, T2, T3 prime, and then it will send those tokens for the large model for verification. So the large model will verify the correctness of those proposed tokens. So in the example here, right, a single forward pass of the large model generate like more than one token. It say T1, T2 is correct, T3 prime is incorrect. So in a single forward pass of the large model, we generate more than one token. This reduces the like token generation latency compared to the like one token per forward pass. And the vLLM is a system that natively supports continuous batching. So how does speculative decoding work with continuous batching? So actually it's pretty simple. So we will have a draft runner which can propose token like auto-regressively. The draft runner is responsible for running those small model. And then we will send it to the target runner, which will run the large model for verification. So the large model will tell us, oh, which token is correct, which token is incorrect. It will also generate some like bonus token. Basically tells us, oh, if it will correct the last incorrect token or generate one extra token if all the proposed tokens are correct. And in the next iteration, we will resume from the bonus token. So to implement speculative decoding in vLLM, we change the scheduler so that the scheduler can schedule more than one memory slot for each request. We also change the memory management to manage the KV cache for both the small model and the large model. And the speculative decoding worker is responsible for like calling the draft worker to propose tokens, the target worker to verify like which tokens are correct, which tokens are incorrect, and also the rejection sampler is responsible to generate the final output. So we try to make the framework as general as possible. So we have different flavors of like speculative decoding, which I will dive into in the next slide. So the most standard speculative decoding we have is a draft model-based speculative decoding. Basically, we use a small model to speculate the large model. And there are some commonly seen model pairs like Llama 68M to speculate 7B model, 7B model to speculate a 70B model. But one challenge in this case is like, how do you find a good draft model? So to be very honest, we haven't found a good draft model for a 8B for Llama 3 8B. So we could not use the Llama 2 small model like for the Llama 3 because they have different vocabulary size, and speculative decoding requires that they have the same vocabulary. So that's why in vLLM, we also support like draft model-free speculation methods. So the first type of draft model-free speculative decoding we support is prompt lookup decoding. So prompt lookup decoding, let me give you a very quick example. So given the prompt, like what is the capital of South Korea, we will generate all the possible 2 grams and all the tokens, all the tokens that follow the 2 gram, right? Like the token after what is the capital of. So during the generation phase, when we see the 2 gram, like when we see the capital, we look up it in the lookup table, and if we find a match, we will just propose the tokens based on the value we store in the lookup table. So like the example here, we find, oh, the of South Korea might be the following tokens, and luckily they are all guessed correctly. So in that case, in a single forward pass, we generate 3 tokens. So prompt lookup decoding works pretty well for those like summarization, question answering data set, where like the output has a big overlap with the input. We also support like other like Medusa, Eagle, MLP speculator, like those type of speculation methods. So instead of using a small model, they have some additional layers or additional heads to propose tokens. So what's the performance? How good is speculative decoding it is? So we benchmark those methods, and the first one is draft model-based speculative decoding. So the blue bar is with speculative decoding, the red bar is original. Like without any, without speculative coding. We find that it can improve the performance, like bring up to 1.5x speed up at QPS1. We also benchmark those n-gram speculative decoding method, and we find that it can bring up to 2.8x speed up when the QPS is small. But that's not the end of story. So during the integration of speculative decoding, we find that sometimes when the QPS is high, it can actually slow down the performance. So this is a full picture actually. So when the QPS is like say 10, we find that it brings like 1.4x slowdown, 1.x slowdown on the 2 data sets. So it tells us that speculative decoding is not always beneficial. So let me give you some intuition behind the slowdown. So in the example here, we have 3 requests, and we propose 2 tokens for each request. So there are in total like 9 input tokens. And after the verification, we find that only 1 of them is correct, and we generated 4 tokens, including the bonus token, with computing 9 tokens. So we are wasting 5 tokens here. We are wasting some compute here. So this type of waste is fine because we know when QPS is low, LLM inference is memory bound. But when the QPS is high, it becomes compute bound, and such waste can be very expensive. And instead of doing speculative decoding, you might just want to do normal decoding. In that case, you are generating 9 tokens with computing 9 tokens. You don't waste any compute here. So this motivates some like ongoing research within vLLM. So we propose some like dynamic speculative decoding. It can dynamically adjust the proposed length based on the system load and speculation accuracy. So we are doing like even step level, different generation steps have different proposed lengths, or even request level. So on the high level, it's just when the system load is high, we do less speculation, and when the acceptance rate is high, we kind of do a little bit more speculation. But I encourage you to check our paper for detail if you are interested. But the goal here is we really want to enable the speculative decoding feature in production. So basically, it means it should always improve the performance instead of degrading the performance. And to use it in vLLM, you just need to specify what's the speculative model you want to use and what are the number of tokens you want to use. And similarly, like for n-gram, you just change the speculative model into n-gram. Okay, we talk a lot about speculative coding. I think now let me give you a summary. So I think vLLM is a popular LLM inference engine with broad model support and rich features. It leverages Torch Compile to ensure high performance, and it efficiently supports various speculative decoding methods. So we really hope and we are really grateful for the community to contribute so much and so many users to use vLLM, report the issues, and we are actively working on this project to, we hope it can be better in the future. Thanks for listening, that's all.